Hello there, and welcome to the Sleepy Science Channel. I'm so glad you found your way here. Perhaps you've had a long day. Or maybe you just like to fall asleep while thinking about the stars, rather than counting sheep. Either way, this video is for you. Let your body sink into rest, your breath slow, and your mind grow lighter, as if gravity itself has softened. Tonight, we turn to cosmology, the miraculous story of our universe. From the very first spark of light to the birth of giant galaxies, it is a tale of vastness, mystery, and wonder. Some of what you hear may surprise you, or simply spark a gentle sense of curiosity as you drift off to sleep. And if these calm explorations bring you peace, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, let's begin. The early universe may have been filled with light so dense it behaved like matter. In the very first instance after the Big Bang, the universe was not dark, and it was not empty. Instead, it was radiant. Photons, the particles of light, are packed so closely together that they could not move freely. They scattered constantly, colliding with particles of matter and with each other. This dense ocean of light created pressure, almost as if light itself were a physical substance with weight and texture. Over time, as the cosmos expanded and cooled, photons slipped free, streaming into space as the cosmic microwave background that still surrounds us today. That faint glow is the stretched-out remnant of a universe once so bright it behaved like matter itself. Some regions of the cosmos may still be inflating, forever cut off from us. Cosmic inflation is the idea that, in its first fraction of a second, the universe expanded faster than the speed of light. According to some models, inflation never stopped everywhere at once. Instead, it may continue eternally in distant pockets, creating new regions of spacetime forever. These inflating domains would expand so quickly that no light could ever cross the gulf between them and us. In this picture, our universe is just one bubble among countless others, each sealed off by the runaway expansion of space. We will never see those regions, never touch them, and yet they might exist, endlessly budding into the void. To think that our entire observable cosmos could be just one finite blossom on an infinite tree is both humbling and strangely beautiful. Black holes could carry imprints of the universe's first moments. Black holes are usually thought of as the graves of stars, but some might be older than any star. Cosmologists propose the idea of primordial black holes, formed in the chaos of the early universe. If density fluctuations in that fiery first second were strong enough, whole regions of space could have collapsed under their own gravity before atoms, stars, or galaxies ever existed. Such black holes would carry with them clues to conditions right after the Big Bang. They could be as tiny as mountains, or as massive as stars, hidden across the universe like relics of creation itself. If discovered, they would be time capsules, holding secrets of a universe younger than a heartbeat, when physics itself may have followed rules different from those we know today. Time near the Big Bang may have flowed differently than it does now. Time feels steady to us, each second ticked off evenly, one after another. But near the Big Bang, things may not have been so simple. General relativity tells us that time and space are woven together, and their behavior depends on energy and gravity. In the seething furnace of the early universe, densities and energies were unimaginably high. Time itself may have stretched, warped, or slowed compared to the flow we experience today. Some theories suggest that what we call the beginning of time may not even have been the true beginning, but a transformation from one state to another. When we look back across billions of years, we may not just be peering through space, but also through changing rivers of time itself. The largest known structure in the universe is a billion light-year-long wave of galaxies. The universe is not uniform. Galaxies are not scattered randomly like dust, but instead form vast patterns, threads, walls, and filaments. One of the most extraordinary of these is the Boss Great Wall, discovered in galaxy surveys. It is a sprawling chain of superclusters extending across nearly a billion light-years. Within it, galaxies are strung together like glowing beads on invisible strings of dark matter. To put its scale in perspective, if our Milky Way were a single dot on a map, this wall would stretch across entire pages. These structures remind us that the cosmos is not just vast, but also deeply patterned, a kind of architecture on the grandest imaginable stage. Neutrinos from the first second of creation are still streaming through your body. Neutrinos are ghostly particles, almost without mass, that rarely interact with matter. Trillions of them pass through your body every second, unnoticed. Many of these are made in the sun or distant stars, but some are unimaginably older. In the first second after the Big Bang, neutrinos flooded the universe. Unlike photons, they slipped free early because they interact so weakly with matter. They have been flying through space ever since, forming what physicists call the cosmic neutrino background. Though they are nearly impossible to detect, they are everywhere, including inside you right now. Each one is a relic of the universe's very first heartbeat, still whispering through the cosmos, almost 14 billion years later. Entire galaxies may be moving because of hidden masses beyond the observable edge. Astronomers have noticed that some galaxies are not drifting in the directions we'd expect. Instead, they seem to be tugged along by a hidden influence, something lying far beyond the part of the universe we can see. This motion has been nicknamed the dark flow. It may be caused by enormous masses outside our cosmic horizon, invisible but powerful enough to bend the paths of whole clusters of galaxies. We cannot observe these hidden regions directly, but we see their fingerprints in the motions of galaxies closer to us. It is a reminder that the observable universe is just a patch of something larger, and that unseen structures may still shape the cosmos we live in. The vacuum of space may not be empty, but simmering with quantum energy. When we picture empty space, we often imagine nothingness, a true void. But according to quantum theory, even the vacuum is restless. Tiny particles blink in and out of existence, borrowing energy from uncertainty itself before disappearing again. This restless sea is called the quantum vacuum, and it may hold the key to one of cosmology's greatest mysteries, dark energy. The accelerating expansion of the universe could be driven by the energy of this empty space. In that sense, every cubic inch of apparent nothingness is alive with possibility, buzzing invisibly with the physics that shapes the fate of the cosmos. Patterns in the cosmic microwave background hint at ripples from before the Big Bang. The cosmic microwave background is the oldest light we can see, released when the universe was only hundreds of thousands of years old. To the eye, it looks almost uniform, but sensitive maps reveal tiny variations, ripples less than 1 part in 100,000. These patterns seeded the galaxies, stars, and planets we know today. But some of the ripples are stranger, unusually cold or unusually aligned, pointing to possible physics before the Big Bang itself. They may be scars left from collisions with other universes, or echoes of exotic fields that shaped inflation. The faint patterns in this ancient light are not just random noise. They may be the fingerprints of realities far older and larger than our own. The fate of the universe might depend on particles we haven't discovered yet. The destiny of the cosmos whether it expands forever, collapses back, or drifts into heat death, depends on the nature of its most mysterious ingredients. Dark energy drives expansion, dark matter shapes galaxies, and both may be tied to particles we have never seen. Physicists search for these unseen particles in underground detectors and high-energy colliders, hoping to glue the missing pieces of the puzzle. If they exist, they will tell us whether the universe is stable, whether it may someday decay, or whether it might even cycle through endless rebirths. In the smallest particles may lie the largest answers, hidden keys to the story of everything. Gravity may be weaker than it should be because it leaks into other dimensions. We think of gravity as universal, binding planets to stars and stars to galaxies. But compared to the other forces of nature, it is astonishingly weak. A small magnet can lift a paperclip against the pull of the entire Earth. Some physicists wonder if gravity feels weak because it isn't confined to our familiar universe. Instead, it may spread into hidden dimensions, unseen by us. If true, this would mean the force we experience is only a faint echo of a deeper reality. These extra dimensions could be curled up, too small for us to perceive, yet large enough to siphon away gravity's strength. It's a hypothesis that may explain why the cosmos holds together the way it does, and a hint that our universe could be part of something more layered than we can imagine. The cosmic horizon hides regions of the universe we can never reach. When we look out into the sky, we are really looking back in time. But there is a limit, a boundary called the cosmic horizon. Beyond this line, light has not had enough time to reach us since the Big Bang. Those regions of space are real, filled with galaxies, but they are forever hidden. The horizon is not a wall, but a limit of perspective, like standing on a shore and seeing only as far as the curve of the Earth. Every year, the horizon grows as light from farther reaches finally arrives, yet space itself expands too, pushing other regions beyond our view. The cosmic horizon is a quiet reminder. No matter how far our telescopes stretch, there will always be more universe beyond, forever out of sight. Primordial black holes could be as small as atoms, or as heavy as mountains. Most black holes form when stars collapse, but there may be older, stranger ones, primordial black holes. Born in the first moments after the Big Bang, they could be wildly different from the black holes we know today. Some may be tiny, with event horizons smaller than an atom, while others could weigh as much as mountains. Over billions of years, the smallest would have evaporated through Hawking radiation, but others might still drift invisibly through the cosmos. If they exist, they could even make up some or all of the mysterious dark matter. These hidden relics would be scattered everywhere, silent fossils of creation itself, so subtle that a primordial black hole could pass through Earth unnoticed, and so powerful that collectively they may shape the destiny of galaxies. The early universe may have birthed cosmic strings stretching across space. Theories of high-energy physics predict that as the universe cooled from its hot beginning, strange defects in spacetime could have formed, infinitely thin but immensely powerful. These are called cosmic strings. Unlike ordinary strings, they are not matter at all, but cracks in spacetime itself, stretching potentially for billions of light-years. If two cosmic strings were to cross, they could snap and release bursts of gravitational waves, ringing through the universe like struck chords. Though none have yet been found, their existence would reveal physics far beyond what we know. The idea that the early universe might still hold hidden filaments, invisible to our eyes but etched into the fabric of space, is both haunting and beautiful, like scars from the cosmos's own birth. Ripples in space-time could be fossils from the very first instant. Gravitational waves are ripples in spacetime, stirred up by events like colliding black holes. But there may also be far older waves, born in the very first instant of the universe. During cosmic inflation, spacetime itself may have shivered with quantum fluctuations, stretching those ripples across the entire cosmos. These primordial gravitational waves would be unimaginably faint, but if we could detect them, they would be direct fossils of the universe's birth. Unlike light, which only became free hundreds of thousands of years later, these ripples would carry us back almost to time zero. Scientists search for them in delicate patterns of polarization in the cosmic microwave background, hoping to hear the faintest whispers of creation's first breath. Some galaxies may be racing toward a mysterious great attractor hidden in space. Our galaxy, along with many others, is not just drifting aimlessly. It is being pulled toward a region of space called the Great Attractor. This hidden mass lies hundreds of millions of light-years away, shrouded behind the dust of the Milky Way, making it difficult to study. Galaxies across vast distances show a shared motion, as though they are sliding down the slope of some invisible gravitational hill. The true nature of the Great Attractor is still uncertain. It may be a concentration of galaxy clusters, or something even larger. Whatever it is, it exerts a pull strong enough to guide the paths of entire galaxies, including our own. We are moving toward it even now, carried along on the slow current of cosmic gravity. Dark energy might grow stronger with time, changing the universe's destiny. Dark energy is the mysterious force driving the accelerated expansion of the universe. For now, it seems steady, but what if it changes? Some models suggest that dark energy could grow stronger over billions of years. If that happens, the expansion would accelerate more and more, tearing galaxies apart, then stars, then even atoms in a catastrophic big rip. In other scenarios, dark energy could fade, allowing gravity to slow expansion or even reverse it. Because dark energy makes up most of the cosmos, its behavior determines everything about the future. And yet, for now, we do not know if it is constant or evolving. The entire fate of the universe may rest on the hidden nature of this invisible force. Cosmic voids, vast expanses with almost no galaxies, are still expanding. Between the luminous filaments of the cosmic web lie immense empty regions called voids. These can span hundreds of millions of light-years and contain only a handful of galaxies. Voids are not static emptiness, though. They are expanding faster than the rest of the universe as matter flows outward toward denser regions. In a way, they are the growing hollows of the cosmos, ballooning as galaxies drift away. By studying these voids, scientists can test the nature of dark energy and cosmic expansion. For now, they remain among the quietest and loneliest regions of the universe, vast oceans of near-nothing, still stretching wider as time moves on. The universe's geometry may be ever so slightly curved. When we think of the universe, we often picture it as flat, stretching endlessly in all directions. But geometry in cosmology is subtle. Depending on its total energy, the universe could be positively curved, like a sphere, or negatively curved, like a saddle. Observations suggest it is astonishingly close to flat, so close that if there is curvature, it is too small to detect with certainty. A universe with even the tiniest curvature would, over unimaginable distances, bend light in ways that reveal its shape. For now, we live in a cosmos that feels flat, but cosmologists keep searching for that faint, hidden curve that could tell us more about its ultimate size and fate. The cosmic microwave background is dotted with strange cold spots. The cosmic microwave background, the afterglow of the Big Bang, is mostly smooth and uniform. Yet here and there, it contains unusual features, patches colder than expected. One of the largest is known simply as the cold spot, a region of the sky where the temperature of this ancient light dips strangely low. Some suggest it may be caused by a massive void in that direction, sapping energy from photons as they pass through. Others speculate it could be a fingerprint of physics beyond the known universe, perhaps even the scar of a collision with another cosmos. Whatever its cause, the cold spot remains one of the most puzzling anomalies written in the universe's oldest light. The first stars may have been hundreds of times heavier than the Sun. In the quiet after the Big Bang, the universe was dark. Then hydrogen and helium gathered into the very first stars. These were nothing like the stars we see today. With no heavier elements to cool the gas, they grew enormous, hundreds of times the mass of our Sun. The light was intense, blazing white-blue, and they lived fast, burning through their fuel in only a few million years. These population 3 stars forged the very first heavier elements, carbon, oxygen, and iron, in their cores. When they died, they scattered those elements across space, seeding the raw material for later generations of stars, planets, and eventually life. Though none remain today, every atom of carbon in your body may once have been born in one of these long-vanished giants. Some of those stars may have collapsed into the first black holes. The most massive of the first stars ended their short lives in collapse. Their gravity was so strong that when their fuel ran out, no force could stop them from imploding. Some exploded as supernova, leaving behind neutron stars, while others fell directly into black holes. These black holes were unique, not the corpses of ordinary stars, but the direct descendants of the first cosmic fire. They may have acted as seeds, growing over billions of years into the supermassive black holes that anchor galaxies today. If so, the brilliant quasars we see at the edge of the observable universe, powered by black holes a billion times the Sun's mass, may trace their lineage all the way back to those first collapsing stars born in the dawn of Calor. Time. The Milky Way moves through space at over 1 million miles per hour. Though the night sky looks still, our galaxy is on a ceaseless journey. The Milky Way, along with its stars, planets, and nebulae, drifts through the cosmic web at more than 1 million miles per hour. This motion is partly the result of local gravitational pulls, from nearby galaxies, from clusters, even from vast unseen structures. To us, it feels invisible, since everything around us moves together. But when astronomers measure the cosmic microwave background, they can see a faint dipole pattern, a subtle distortion caused by our galactic motion. It's a reminder that there is no absolute rest in the universe. Everything drifts, everything flows, carried along in the great cosmic tide. Superclusters of galaxies weave a cosmic web across the universe. Galaxies do not sit alone in space. They gather into clusters, and those clusters gather into larger structures, superclusters. These superclusters stretch for hundreds of millions of light years, linked by filaments of galaxies and separated by vast cosmic voids. Together, they form the cosmic web, a pattern that resembles strands of a spider's web or the filaments of neurons in a brain. Our own galaxy lives within the Laniakea supercluster, a sprawling region that contains hundreds of thousands of galaxies. When we map these structures, we see not chaos but elegance. Gravity sculpting luminous threads across the universe, revealing a hidden order that spans billions of light years. Ancient quasars shine from less than 1 billion years after the Big Bang. Quasars are the beacons of the early universe, galaxies whose central black holes feed so voraciously that they blaze brighter than all their stars combined. Some quasars we see today come from less than 1 billion years after the Big Bang, when the cosmos was still young. To shine so brightly so soon, their black holes must have grown with astonishing speed, reaching masses of 1 billion suns in a fraction of cosmic history. These quasars act like lighthouses, illuminating the fog of intergalactic gas and helping us peer back into the reionization era, when galaxies first carved light into the darkness. Their existence poses deep questions. How did black holes grow so fast? And what seeds gave rise to them? We may live in a local bubble of unusually empty space. Astronomers mapping the interstellar medium have discovered that our Sun lies within a vast cavity, a bubble carved into the galaxy's gas. This local bubble stretches hundreds of light years across and is unusually empty compared to its surroundings. It was likely created by a chain of supernova explosions millions of years ago, which blew away the surrounding material. Today, our Sun and its neighbors drift quietly within this rarefied zone, bathed in a faint glow of hot plasma. The edges of the bubble form denser walls of gas and dust where new stars are born. To think that our solar system resides inside the lingering footprint of ancient stellar deaths adds a strange intimacy to our place in the cosmos. Dark matter may clump into invisible filaments that shape galaxies. When astronomers simulate the growth of the universe, they find that ordinary matter alone cannot form the patterns we see. Something unseen, dark matter, must weave invisible scaffolding beneath it all. In these simulations, dark matter clumps into filaments stretching across space, guiding the flow of galaxies into strands and knots. Our own Milky Way sits within one of these invisible filaments, like a dewdrop caught on a spider's thread. We cannot see the dark matter directly, but we see its gravity sculpting the grand architecture of the universe. Without it, galaxies would fly apart, and the cosmic web would unravel into scattered fragments. Actions, if they exist, could make up all dark matter. Dark matter's true identity is still unknown, but one candidate is the action, a hypothetical particle predicted by certain theories of quantum physics. Unlike heavy particles once imagined to explain dark matter, actions would be incredibly light, lighter even than neutrinos, but produced in such enormous numbers that together they could outweigh all the visible matter in the universe. Actions would interact so weakly that they slip through stars, planets, and even detectors unnoticed. Scientists have built experiments with ultra-sensitive magnetic fields and resonant cavities, hoping to catch even a whisper of these elusive particles. If found, actions would not only solve the dark matter mystery, but also connect cosmology with deep questions of particle physics. The laws of physics may be slightly different in other universes. Some versions of inflation predict that our universe is only one bubble in an endless multiverse. If so, the laws of physics may vary from bubble to bubble. In one, stars might never form because gravity is weaker. In another, atoms may not exist at all. Our own universe appears finely tuned, its constants balanced in a way that allows galaxies, chemistry, and life. It raises a haunting possibility. Perhaps we live in one universe among countless others, most sterile, some chaotic, but ours balanced just enough for complexity to bloom. Though we cannot see beyond our cosmic horizon, the idea that reality may be broader than our laws allows us to wonder at the fragile conditions that make existence possible here. Cosmic inflation could have spawned an infinite multiverse. In the theory of eternal inflation, the universe expands not as a single bubble, but as an endless froth. Regions of space stop inflating and form universes like ours, while other regions keep expanding, forever spawning new bubbles. Each bubble could be infinite in size, and together they form a multiverse without end. In this picture, The Big Bang was not the beginning of everything, but simply the birth of our local region. Other universes may lie forever beyond our reach, with their own physics, their own galaxies, and perhaps their own forms of life. It is a vision of reality so vast that even our observable cosmos, with its 2 trillion galaxies, would be just one small ripple on an endless cosmic sea. The universe once transitioned from opaque to transparent. For its first few 100,000 years, the universe was a fog of particles. Electrons and protons drifted free, scattering photons so completely that light could not travel. It was a glowing plasma, opaque to vision, with no way for radiation to move freely. Then, as the cosmos cooled, electrons settled into orbits around protons, forming the first atoms. Suddenly, photons were released, able to fly unhindered across space. In that instant, the universe became transparent, and the light we call the cosmic microwave background began its journey. Every time we measure that ancient glow, we are seeing the moment the universe first let light go free, a timeless after-image of a cosmos lifting its primordial veil. The reionization era lit up space with the first galaxies. After recombination, the universe was transparent but dark, filled only with neutral hydrogen gas. For hundreds of millions of years, there were no stars to shine. Then, slowly, the first galaxies ignited. Their newborn stars and quasars flooded space with ultraviolet light, energetic enough to break hydrogen back into ions. This period is called the reionization era, when the fog lifted once more, not by cooling this time, but by being pierced with light. Reionization carved great bubbles of transparency around the first galaxies until the whole universe was lit. When we observe distant galaxies and quasars today, we are catching sight of that moment when darkness gave way to cosmic dawn and the universe became illuminated from within. The cosmic neutrino background has never been directly seen. We know of the cosmic microwave background, the light from when the universe became transparent. But before that, another background formed, a sea of neutrinos, released only seconds after the Big Bang. These ghostly particles still stream through space today, forming the cosmic neutrino background. Unlike photons, which were trapped for hundreds of thousands of years, neutrinos escaped almost instantly, carrying information from the universe's earliest heartbeat. Yet because they interact so weakly, we have never directly detected them. They flow through planets, stars, and our bodies, almost without trace. Instruments capable of catching even a faint echo are still being dreamed of. If one day detected, this neutrino background would be like opening a hidden window into the first second of existence itself. The most energetic particles in the universe may come from beyond our galaxy. Cosmic rays are high-energy particles that rain down on Earth, striking our atmosphere with invisible sparks. Most come from sources within our galaxy, like exploding stars. But some cosmic rays carry energies so extreme that no known event in the Milky Way could have launched them. These ultra-high-energy cosmic rays may come from far beyond, perhaps the jets of distant quasars or collisions between galaxy clusters. Each particle travels for millions or billions of years, until by chance it meets Earth. When it strikes, it unleashes a cascade of secondary particles, momentary fireworks of invisible origin. Even now, we don't fully know what launches the most powerful particles in the universe, only that they come from somewhere far beyond our home galaxy. Black holes might merge often enough to reshape galaxies. Black holes are not always solitary. In galaxies where stars collide and clusters interact, black holes can be drawn into pairs. Over time, they spiral closer, radiating energy in gravitational waves until they finally merge. Each collision creates a single, larger black hole and a burst of spacetime ripples. Over billions of years, these mergers may grow black holes at the centers of galaxies to enormous sizes. When they do, the energy released can alter the flow of gas, shaping star formation and influencing the structure of the galaxy itself. In this way, black hole mergers are not just rare fireworks. They are part of the quiet, ongoing architecture of the cosmos, chiseling galaxies into the shapes we see today. Gravitational waves carry whispers of ancient collisions. Einstein predicted them, and a century later, we finally heard them. Gravitational waves are ripples in spacetime, created when massive objects like black holes or neutron stars collide. They stretch and squeeze space as they pass, though only by less than the width of a proton. With detectors like LIGO and Virgo, scientists have recorded dozens of these events, distant cataclysms billions of light years away, their whispers reaching us across cosmic time. Each wave carries a signature, telling us about the size, mass, and dance of the objects that created it. And someday, if we can hear even fainter ones, we may catch the background hum of gravitational waves from the earliest universe, echoes of creation still rolling through spacetime. The speed of cosmic expansion has changed more than once. The universe does not expand at a constant pace. In its first fractions of a second, inflation drove an almost unimaginable expansion, faster than light. After that, gravity slowed things down, as matter pulled against the outward flow. For billions of years, galaxies drifted apart at a gentle rate. But in the last few billion years, the expansion has sped up again, pushed by dark energy. This shifting pace tells us that the cosmos has gone through phases, each governed by the balance of forces and energies within it. From rapid inflation to slow deceleration to the present acceleration, the rhythm of expansion is like a cosmic heartbeat, changing with time and still unfolding into an unknown future. Some stars may have formed directly from collapsing dark matter. Ordinary stars form from collapsing clouds of gas, but some theories suggest a stranger origin story, dark stars. In the early universe, dark matter may have clumped densely enough that its annihilation released bursts of energy. Instead of collapsing fully, these clumps could inflate into giant dark stars, powered not by fusion, but by dark matter itself. They may have been massive, glowing faintly with heat from within, but unlike ordinary stars, their light would have been almost invisible to us. If such stars existed, they could have been the first beacons of the cosmos, later collapsing into black holes that seeded galaxies. Though still hypothetical, the idea of stars born from the invisible matter of the universe gives a haunting glimpse of what might once have been. The cosmic microwave background is slightly lopsided. When we map the cosmic microwave background, the afterglow of the Big Bang, we find it is almost perfectly uniform. Almost, but not entirely. There is a slight asymmetry, a lopsidedness, with one side of the sky showing slightly stronger fluctuations than the other. This imbalance is puzzling, because the early universe should have been nearly the same in every direction. Some explanations suggest it is simply a statistical quirk, others propose deeper causes, like hidden physics from inflation, or even interactions with regions beyond our observable universe. Though subtle, this lopsidedness challenges our assumption that the cosmos is perfectly isotropic, and it keeps cosmologists searching for the hidden story behind this ancient light. A mysterious axis of evil aligns structures across the universe. Among the patterns of the cosmic microwave background, scientists have noticed something unusual, large-scale features that seem to align along a common axis in the sky. This alignment, strangely nicknamed the axis of evil, shouldn't exist if the universe is truly random and uniform at the largest scales. Even more puzzling, some of the largest cosmic structures, like galaxy distributions, seem to follow this same orientation. Whether it is a coincidence, a statistical fluke, or a sign of unknown physics, no one knows. The name may be playful, but the mystery is serious. Why should the universe, so vast and ancient, show a preference for any particular direction at all? The finite tuning of cosmic constants allows galaxies to exist at all. The universe is balanced on a razor's edge. The strength of gravity, the charge of the electron, the mass of fundamental particles. If any of these values were even slightly different, the cosmos would look nothing like it does today. Stars might never ignite, atoms might never form, or galaxies might collapse too quickly to allow life. This delicate balance is known as fine-tuning, and it fascinates cosmologists because it seems improbably precise. Some see it as a mystery to be explained by deeper laws of physics. Others suggest the multiverse, where countless universes exist with different values, and we live in the one where conditions happen to allow observers. Whatever the explanation, it is humbling to know that the entire visible universe, from the largest galaxy to the breath in your lungs, depends on the delicate tuning of invisible constants written into the fabric of reality. Some physicists believe the universe is a hologram. It sounds like science fiction, but the holographic principle is a serious idea in theoretical physics. It suggests that everything in the universe, stars, galaxies, even ourselves, might be described not in 3 dimensions, but by information encoded on a distant 2-dimensional surface. Just as a flat hologram contains the illusion of depth, the cosmos we live in may emerge from data written on a cosmic boundary. This strange idea comes from studying black holes, where information appears to be stored on the event horizon rather than inside. If true for black holes, it could be true for the whole universe. The holographic principle doesn't mean reality is an illusion, but that space and time themselves may be emergent, shadows of a deeper, more fundamental layer of physics. Quantum fluctuations may have seeded every star and planet. In the smallest scales of reality, quantum physics rules, particles flicker in and out of existence, and uncertainty is the law. During cosmic inflation, these tiny quantum fluctuations were stretched to cosmic scales, becoming slight ripples in the density of the universe. Over billions of years, gravity amplified those ripples, drawing matter into some regions more than others. From those seeds grew galaxies, stars, planets, and eventually life itself. It is astonishing to realize that everything we see in the night sky, from the Milky Way to the most distant galaxy cluster, may have been born from microscopic quantum jitter amplified by the vast machinery of Ka. Cosmic expansion. The entire universe, in a sense, rests on the chance tremors of the quantum world. Cosmic inflation could have created baby universes we'll never see. Inflation is the idea that the universe expanded faster than light in its first instant. But some versions of the theory suggest it didn't happen uniformly. Instead, while our region slowed down and became a universe, other regions may have continued inflating, forming their own universes. This process may happen endlessly, with baby universes budding off like bubbles in boiling water. Each one would be cut off from the others by expansion faster than any signal could cross. Some might follow laws of physics very different from ours. Others might look much the same, with galaxies and stars like our own. If true, our observable universe is just one blossom on an infinite cosmic tree, its countless branches forever hidden from one another, each carrying its own version of reality. There may be more galaxies in the observable universe than grains of sand on Earth. The number of galaxies is almost beyond imagination. Early estimates suggested hundreds of billions. But deep-field images from telescopes like Hubble revealed far more. Counting carefully, cosmologists now think there may be 2 trillion galaxies in the observable universe. To give perspective, if you scooped up all the sand from every beach and desert on Earth, the grains would still fall short of the number of galaxies above. Each of those galaxies contains billions or trillions of stars. And each of those stars could host planets, moons, and perhaps life. The scale is so immense that even the word infinite feels close at hand. When we gaze at the night sky, we see only the faintest sprinkling of the cosmic ocean, a handful of nearby sparks among an overwhelming abundance. Some regions of space may have negative energy density. In most of the universe, energy is positive, tied to matter, radiation, and motion. But in quantum field theory, there are scenarios where the energy of space itself could dip below zero, creating regions of negative energy density. These exotic states are not like ordinary emptiness. They could warp spacetime in unusual ways, potentially allowing shortcuts like wormholes or even stable warp bubbles. Though still theoretical, negative energy has been glimpsed in tiny effects, such as the Casimir force between closely spaced plates in a vacuum. If it can exist in small ways, perhaps it can exist in larger cosmic contexts. Negative energy density could be one of the strangest hidden features of the universe. Rare, fleeting, but profound enough to reshape our understanding of what nothing really means. Primordial black holes could explain dark matter. Dark matter remains one of the great mysteries of cosmology, invisible, undetectable except by its gravity. One possibility is that dark matter isn't made of particles at all, but of black holes formed in the first moments after the Big Bang. These primordial black holes could range in size from asteroids to stars, scattered throughout the cosmos. Unlike ordinary black holes, they would not be the end state of dying stars, but fossils of the universe's earliest fluctuations. If enough of them exist, they could account for all the dark matter we see shaping galaxies and clusters. Detecting them would not be easy. They could drift unseen through space, giving themselves away only through rare gravitational effects. If confirmed, primordial black holes would tie 2 of the universe's greatest mysteries together in a single explanation. A single photon could, in theory, stretch across the whole universe. Photons, the particles of light, are described by waves. And in principle, a single photon's wave can extend indefinitely, stretching across vast distances. In the expanding universe, light from the earliest times has been redshifted to longer and longer wavelengths. Some of the photons from the cosmic microwave background now have wavelengths measured in millimeters. Small, but not infinitely so. In theory, though, a photon could be spread so thin that its wave function spans the entire observable universe. This is not something we can observe directly, but it shows how strange quantum mechanics becomes on cosmic scales. Even a single particle of light might not be local, but universal, rippling silently across billions of light years. Entropy ensures the cosmos will one day reach heat death. Entropy is the tendency for systems to move from order to disorder. On Earth, it's why energy disperses and why things break down over time. On the scale of the cosmos, entropy ensures that stars will eventually burn out, galaxies will drift apart, and usable energy will vanish. In the far future, trillions upon trillions of years from now, the universe may reach heat death, a state where all is cold and uniform, with no gradients left to drive change. It is not a fiery ending, but a fading, a slow dissolution into silence. Though it sounds bleak, it is also deeply peaceful. A universe that once blazed with energy, gently settling into perfect stillness. Vacuum decay could, in principle, erase the universe instantly. According to some interpretations of particle physics, the vacuum state of our universe may not be perfectly stable. If it is metastable, then one day, perhaps in billions of years, perhaps tomorrow, a tiny bubble of true vacuum could form. Expanding at nearly the speed of light, it would erase everything it touched, rewriting the laws of physics as it spread. We would never see it coming. The change would arrive faster than light could warn us. Though the idea sounds terrifying, it is largely hypothetical, and even if possible, the timescales are so vast as to be irrelevant to human existence. For now, it remains one of cosmology's most haunting possibilities, that reality itself may not be permanent, but a delicate balance that could, in principle, collapse. Cosmic rays constantly shower Earth with particles from distant space. Every moment, invisible particles from space rain down on Earth. These are cosmic rays, high-energy fragments of atoms launched by distant supernova, pulsars, or even galaxies far away. Most pass through unnoticed, striking our atmosphere and scattering into showers of smaller particles. Some are so energetic that they challenge our understanding of physics, carrying more power than any particle accelerator on Earth can produce. You are touched by them constantly. They slip through your body, through oceans, even through mountains. In fact, a tiny fraction of the noise in old film photography comes from cosmic rays striking the film. They are a reminder that Earth is not isolated, but bathed in a steady drizzle of particles born in the most violent corners of the universe, still reaching us across immense spans of time and space. The observable universe is only a fraction of the whole. Where we look out into the cosmos, the most distant light we can see comes from around 13.8 billion years ago. Yet because space has been expanding, the observable universe stretches much farther, about 93 billion light-years across. But this is not the full universe, only the patch we can see. Beyond it lies more space, perhaps infinitely more, hidden behind the cosmic horizon. Entire galaxies, clusters, even colossal structures may lie forever outside our reach. Some theories suggest our observable universe is like a bubble in a vast, inflating ocean of space. Others imagine countless bubbles, each sealed from the rest. Whatever lies beyond, we may never know, and yet, just knowing the universe is larger than what we see fills the night sky with mystery. Galaxy clusters collide in slow-motion cosmic crashes. Clusters of galaxies are the largest bound structures in the universe, containing hundreds or thousands of galaxies, plus immense clouds of hot gas. When they collide, the process is slow, lasting billions of years. Galaxies usually pass through without colliding, because space between stars is vast. But their hot gas clouds slam together, heating up and glowing in X-rays, while dark matter halos glide past almost undisturbed. These collisions reshape the clusters, mixing their contents and altering their structures. Some galaxies may be stripped of gas, leaving them to fade into silence. Seen across cosmic time, cluster mergers are like continental drift on Earth, but on unimaginable scales. Slow, inexorable, and transformative, sculpting the architecture of the universe. The bullet cluster provides direct evidence for dark matter. One of the strongest clues for dark matter comes from an extraordinary collision called the bullet cluster. Two galaxy clusters passed through each other, and astronomers studied the aftermath. The visible gas, which carries most of the normal matter, slowed down and piled up, glowing brightly in X-rays. But the galaxies themselves, and more importantly, the gravitational mass revealed by lensing, kept moving ahead. This showed that most of the mass was not in the hot gas, but in something invisible, dark matter. The bullet cluster has become a cosmic laboratory, a snapshot proving that unseen matter outweighs the stars and gas we can see. It is one of the clearest most compelling windows into the existence of the invisible scaffolding that holds the universe together. Some galaxies are so faint they're almost invisible. Not every galaxy glitters brightly in the night sky. Some, called ultra-diffuse galaxies, spread their stars so thinly that they look more like faint smudges than luminous cities of stars. These galaxies may be as large as the Milky Way, but with only a fraction of the stars. They are ghostly, difficult to detect, and often discovered only through sensitive surveys. Some appear to be rich in dark matter, while others strangely seem to lack it almost entirely. Their faintness makes them fragile, easily disrupted by interactions with larger galaxies. Yet their existence reveals that galaxies come in more varieties than we once imagined, from blazing spirals to nearly invisible shadows drifting quietly through the cosmic web. Giant elliptical galaxies may be the fossils of countless mergers. While spiral galaxies like the Milky Way are graceful and structured, elliptical galaxies are huge, rounded, and often dull in appearance. Yet their simplicity hides a dramatic past. Astronomers believe giant ellipticals are the products of countless mergers. Over billions of years, galaxies collide and combine, their orderly spirals shredded into amorphous shapes. Star formation slows as gas is consumed or stripped away, leaving behind old red stars glowing faintly. These galaxies can grow to incredible sizes, containing trillions of stars. In galaxy clusters, they often dominate the center, like massive fossils of an ancient and violent history. To gaze at one is to see not a quiet giant, but the faded memory of countless galactic collisions, written into its smooth, rounded glow. The universe may be shaped by physics we haven't discovered yet. Our best models explain much of what we see, but cosmology still leans on mysteries. Dark matter and dark energy, which together make up 95% of the universe, remain unidentified. Inflation, the theory that explains the cosmos's early rapid expansion, still needs a mechanism. And quantum gravity, the unification of general relativity and quantum mechanics, has yet to be found. It may be that new physics, undiscovered laws, underpin the entire structure of the universe. Each telescope, each experiment, pushes closer to the edge, hinting that reality may rest on foundations we have not yet glimpsed. For now, cosmology stands as a bridge between the known and the unknown, a map sketched partly in discovery and partly in mystery. Wormholes are allowed by relativity, but may never form naturally. Einstein's equations admit strange solutions, tunnels through spacetime, connecting distant regions or even different universes. These wormholes are a staple of science fiction, but they are also legitimate possibilities in general relativity. However, for a wormhole to remain open, it would require exotic matter with negative energy, something we have never seen in large amounts. Without it, wormholes collapse instantly, becoming impassable. Still, they remain a tantalizing thought experiment, a cosmos where shortcuts exist, hidden corridors through the deep fabric of spacetime. Even if nature never built one, wormholes remain a reminder that relativity does not just describe the universe we see, but also strange possibilities that stretch imagination itself. The cosmic web resembles the neural structure of a brain. When scientists map the large-scale structure of the universe, they find galaxies arranged in filaments, knots, and voids, a pattern known as the cosmic web. Strikingly, this structure resembles the network of neurons in a brain. Both systems balance nodes and connections in a way that maximizes efficiency of flow. In the brain, it is electrical signals in the cosmos. It is matter and gravity. The resemblance is not just visual. Mathematically, the two networks share similar properties. To think that the universe, on its largest scales, echoes the same architecture as the mind that contemplates it, is a poetic coincidence, a reminder that patterns repeat, from the smallest sparks of thought to the vast sweep of galaxies. Supervoids may cause subtle distortions in cosmic light. A supervoid is an immense, underdense region of space, larger and emptier than ordinary voids, spanning hundreds of millions of light-years. Though nearly empty, they still influence the light passing through them. Photons traveling across a supervoid lose a little energy, slightly cooling by the time they reach us. This subtle effect, known as the integrated Sachs-Wolf effect, leaves faint imprints on the cosmic microwave background. One possible explanation for the mysterious cold spot is that light passed through such a supervoid on its journey to Earth. Though invisible themselves, supervoids may shape the universe's faintest signals, reminders that even emptiness can leave fingerprints on the oldest light. Some galaxy clusters contain hot gas that outweighs their stars. When astronomers study galaxy clusters, they find that the stars we see make up only a fraction of their mass. Much of the visible matter is locked not in stars, but in immense clouds of superheated gas. This gas glows in X-rays, reaching temperatures of tens of millions of degrees, and it outweighs all the stars in the cluster combined. The gas is held in place by the cluster's gravity, filling the space between galaxies like an invisible ocean. Without X-ray telescopes, we would never know it was there. Its sheer mass reveals that galaxies are not isolated islands, but members of vast ecosystems, immersed in hot, glowing atmospheres. In a sense, the stars are just the brightest sparks within an even greater sea of matter. Black holes may influence the fate of entire galaxies. Though tiny compared to galaxies, black holes at their centers wield enormous power. When they feed, matter spirals inward, heating up until it releases torrents of radiation and powerful jets. These outbursts can blow gas out of the galaxy, shutting down star formation, or stir it, triggering new stars to form. Over billions of years, the activity of a single supermassive black hole can regulate the growth of its host galaxy. Observations suggest that the mass of central black holes and the properties of galaxies are tightly linked, as if they grow together, shaping one another's destiny. Black holes, once thought to be destructive outliers, are now seen as key architects of the cosmic landscape. Time may pass at different rates in different cosmic regions. Einstein's theory of relativity showed that time is not absolute. It bends and flexes with gravity and motion. In regions near massive objects, time passes more slowly in emptier. Weaker gravity regions, it passes faster. On cosmic scales, this means the flow of time may differ slightly from place to place. Even the expansion of the universe itself stretches time, altering the pace at which distant galaxies evolve compared to our local frame. When we look at the cosmos, we are not just peering across space, but across different rivers of time, each flowing at its own tempo. The night sky is therefore not a single snapshot, but a patchwork quilt of timescales, woven together into the cosmic story. The speed of light sets a limit on what we can know. Light is fast, nearly 300,000 kilometers per second, but it is not infinite. Because of this, we see distant galaxies not as they are today, but as they were billions of years ago. The farther we look, the further back in time we reach. The speed of light creates a natural boundary to our knowledge, the cosmic horizon. Beyond it, light has not yet had time to arrive. This limit is not just technological, but fundamental. No future telescope can reveal what lies past it. We live within this light-bound bubble, able to peer into the past, but never beyond a certain edge. The speed of light, so constant and universal, becomes not just a property of physics, but a cosmic boundary on human understanding. The Planck era, the universe's first fraction of a second, remains a mystery. Cosmologists can describe the universe from a fraction of a second onward, but the very first instant, known as the Planck era, remains hidden. In this unimaginably brief sliver of time, less than 1/10 trillion trillionth of a second after the Big Bang, the universe was so hot and dense that our current physics breaks down. Gravity, quantum mechanics, and energy were entwined in ways we cannot yet model. To understand this era would require a complete theory of quantum gravity, uniting relativity with the quantum world. For now, the Planck era is a blank space on our cosmic timeline, a hidden prologue of the universe's story. Whatever happened then determined everything that followed, yet it remains one of the deepest mysteries in all of science. Hawking radiation could one day evaporate black holes. Black holes seem like eternal prisons, swallowing everything that comes too close. But Stephen Hawking showed that they are not perfectly black. Quantum effects near the event horizon allow them to emit tiny amounts of radiation. Over unimaginable timescales, this Hawking radiation slowly saps their mass. For stellar black holes, the process is far too slow to matter now. But given trillions upon trillions of years, they will eventually evaporate entirely, leaving behind nothing but faint radiation. Even the supermassive black holes at the hearts of galaxies will one day fade away. In the far future, when the stars have burned out, Hawking radiation will be the last whisper of the cosmos, black holes gently dissolving into silence. White holes are a possible mirror image of black holes. If black holes are regions where nothing can escape, then white holes are the opposite, regions where nothing can enter. They are mathematical solutions to Einstein's equations, mirror twins of black holes. A white hole would spew matter and light but resist anything trying to cross its horizon. None have ever been observed, and most physicists doubt they exist in nature. Still, they are fascinating hypotheticals. Some theories even suggest black holes could transform into white holes at the end of their lives, releasing information back into the universe. Though purely speculative, white holes are reminders of how strange and flexible relativity can be, allowing possibilities that stretch the imagination far beyond the familiar. Some theories predict a cyclic universe that dies and is reborn. Not all cosmologists believe the universe began once and for all with the Big Bang. Some models suggest a cycle: expansion, collapse, and rebirth. In this view, the universe grows for billions of years, then slows and reverses, collapsing back into a big crunch. From that collapse, a new Big Bang might arise, beginning another cycle. This idea is ancient, echoed in myths of eternal return, but it also has modern scientific versions. Though evidence for a cyclic universe is uncertain, the possibility is haunting, that the cosmos is not a singular story, but an endless loop of deaths and rebirths, each universe following another, perhaps forever. A big crunch could one day reverse cosmic expansion. If the pull of gravity is strong enough, it could eventually halt the expansion of the universe and reverse it. Galaxies would slow, then begin to collapse inward, the cosmos shrinking back on itself. Stars would crowd closer, galaxies would merge, and temperatures would rise. Eventually, everything would converge in a final collapse, a big crunch, undoing the Big Bang. For now, evidence suggests the opposite, that expansion is accelerating under dark energy. But the Big Crunch remains one possible fate, a cosmic implosion that would erase the universe we know, perhaps setting the stage for something new. The Big Bounce could mean our universe is not the first. Some cosmologists combine the ideas of the Big Bang and the Big Crunch into a larger cycle, the Big Bounce. In this model, each universe collapses, then rebounds into expansion again, like a heartbeat of creation. If true, ours is not the first universe, but just the latest in an endless chain. Each bounce may leave traces, imprinted in the cosmic microwave background as subtle patterns or asymmetries. The Big Bounce offers a comforting symmetry, creation and destruction as part of an eternal rhythm, with no true beginning or end. It is speculative, but beautiful. The cosmos breathing in and out forever, with our universe as just one breath among infinite others. Cosmic background radiation once glowed bright orange in the sky. The cosmic microwave background is faint today, just a whisper of cold light at 3 degrees above absolute zero. But in the early universe, it would have looked very different. Billions of years ago, this radiation was still warm enough to glow in visible light. Had we been there, the entire sky would have shone with a fiery orange glow, a uniform radiance stretching in every direction. Over time, as the cosmos expanded, the light stretched to longer wavelengths, cooling into the invisible microwaves we see today. That ancient orange glow was the universe itself shining before stars, before galaxies, a cosmic dawn painted not by suns, but by space-time itself. The universe cooled as it expanded, allowing atoms to form. At first, the cosmos was too hot for atoms to exist. Electrons and protons roamed freely, unable to bind together. But as the universe expanded, its temperature dropped. Around 380,000 years after the Big Bang, conditions became cool enough for electrons to join with protons, creating hydrogen atoms. With atoms stable, light could travel freely, releasing the cosmic microwave background. This cooling marked the end of the universe's childhood chaos, the moment matter began to take form. Every atom of hydrogen in your body today, every atom in water, in air, in stars, is a direct descendant of that cooling, when the cosmos first settled into structure. Matter barely won over antimatter in the beginning. In the earliest moments of creation, particles of matter and their antimatter twins were produced in nearly equal amounts. When they meet, matter and antimatter annihilate, leaving behind only energy. Had the amounts been perfectly equal, the universe today would contain no galaxies, no stars, and no people, only light. But somehow, matter held the slightest advantage, outnumbering antimatter by just one particle in a billion. That tiny imbalance became everything: the stars, the planets, the oceans, and even us. The mystery of why matter triumphed is still unsolved, but the fact that it did is why anything exists at all. Without that imbalance, no galaxies would exist. It is hard to imagine how fragile reality is. If matter and antimatter had been perfectly symmetrical, their mutual destruction would have erased all substance. The universe would be a thin haze of radiation, glowing forever without form. No stars would ignite, no galaxies would assemble, no planets would form, and no life could arise. Every structure in existence rests on that 1/1000th advantage of matter. We owe our very being to a cosmic imperfection, a tiny skew in the balance that gave atoms, and thus worlds, a chance to exist. The universe as we know it is built not on symmetry, but on the smallest possible break from it. Inflation predicts the universe is nearly perfectly flat. Inflation, the theory that the universe expanded faster than light in its first instant, has another surprising consequence. It smooths and flattens space-time. Just as blowing up a balloon makes its surface appear flatter from up close, inflation stretched the fabric of the cosmos so greatly that today it appears nearly perfectly flat on observable scales. Measurements of the cosmic microwave background confirm this with exquisite precision. To within fractions of a percent, the universe shows no detectable curvature. Whether this flatness extends beyond our horizon or whether the larger universe curves gently like a hidden sphere remains unknown. But in our cosmic neighborhood, inflation left behind a universe astonishingly straight and balanced. Dark flow hints at influences beyond our cosmic horizon. Astronomers studying the motion of galaxy clusters discovered something strange. Many seem to be drifting in the same direction, faster than expected, as though pulled by something beyond the observable universe. This large-scale motion has been nicknamed dark flow. One explanation is that massive structures exist outside our horizon, their gravity tugging on galaxies across billions of light-years. If true, dark flow is not just motion, but evidence that our observable bubble is part of a larger reality, with hidden giants shaping what we see. Though still debated, the idea that unseen structures beyond our cosmic edge are influencing us adds a haunting depth to the night sky. The integrated Sachs-Wolf effect reveals dark energy's fingerprints. Light from the cosmic microwave background does not travel through empty space. It weaves past galaxies, clusters, and vast structures, gaining and losing energy as it moves through gravitational wells. In a universe without dark energy, the balance of gains and losses would cancel perfectly. But observations reveal a small leftover signal, the integrated Sachs-Wolf effect. This tells us that gravitational wells are changing as the universe expands, stretched by dark energy. In this faint way, the invisible hand of dark energy leaves fingerprints on the oldest light. By studying these subtle imprints, scientists confirm not only that dark energy exists, but that it has been shaping the universe for billions of years. The cosmic microwave background once fit inside your hand. Today, the cosmic microwave background fills the entire observable universe, spanning 93 billion light-years. But when that light was first released, the universe itself was only about 1 million light-years across, small enough, in cosmic terms, to fit within your hand. Imagine cradling the whole universe, glowing hot and dense, a sphere of plasma ready to expand into everything we know. That light has traveled ever since, stretched and cooled by expansion, but still present, still whispering its story across the sky. To think that the cosmos we inhabit was once so small is almost impossible, and yet, in its earliest moments, everything really did fit into a graspable whole. Some ancient stars may still burn from the dawn of time. Most of the first stars were massive and short-lived, but a few may have been small, faint, and long-lasting. Stars with very low mass can burn for trillions of years, far longer than the current age of the universe. If any such stars formed in the early cosmos, they could still be shining today. They would be dim, red, and difficult to spot, hidden among the countless younger stars around them. But if found, they would be living fossils of the cosmic dawn, stars that witnessed the birth of galaxies, the rise of black holes, and the long unfolding of cosmic history. Somewhere in the night sky, a faint red ember may still glow, older than any other star we have ever seen. The universe may still echo with the first gravitational waves. Gravitational waves are ripples in spacetime, and some of the first may have been produced during cosmic inflation. These primordial waves would have been stretched across the universe, leaving faint imprints in the polarization of the cosmic microwave background. Detecting them would be like hearing the faint sound of creation itself, vibrations from the universe's earliest instant still ringing today. Though they remain elusive, experiments continue to search for this background hum. If discovered, these waves would confirm inflation, and give us direct evidence of physics at energies we can never reproduce on Earth. The cosmos itself would become the laboratory, still echoing with its birth. The scale of cosmic expansion stretches light into red. As the universe expands, it stretches not only space, but the very light that travels through it. Photons moving across billions of years are pulled to longer, redder wavelengths. This cosmological redshift is how we measure distance to galaxies. The farther they are, the more their light has been stretched. It means that the night sky is a time machine, its colors stretched by the breathing of the cosmos itself. A galaxy that once shone blue may now arrive at our telescopes in shades of red, its energy diluted by expansion. Each photon in your eye tonight is an ancient traveler, drawn out like a musical note played slower and lower, carrying the story of distance, time, and the universe's restless growth. Olber's paradox asks why the night sky is dark. If the universe were infinite, filled uniformly with stars, the night sky should blaze with light in every direction. This simple thought experiment, known as Olber's paradox, puzzled thinkers for centuries. Why then is the sky dark at night? The answer lies in two facts. The universe has a finite age, and it is expanding. Because stars have not existed forever, their light has not had time to fill the sky. And because expansion stretches light into faint, invisible wavelengths, much of it fades beyond our sight. The darkness between the stars is therefore not emptiness, but a canvas painted by time and distance. The night sky glows only with what has had time to reach us. The answer lies in cosmic expansion and finite age. The darkness of the night is not a flaw, but a clue. Expansion means that galaxies recede faster the farther away they are, their light redshifted into invisibility. Finite age means that light from the most distant regions has not yet arrived. Together, these two principles resolve Olber's paradox. The universe is not static nor eternal, but dynamic and young compared to infinity. Each patch of blackness above you is a veil, hiding regions too far or too early for their light to reach. The starless dark is not empty, but alive with light still on its way, destined to arrive only after billions more years have passed. The universe may have begun as a quantum fluctuation. In the strangeness of quantum physics, empty space is never truly empty. Tiny fluctuations in energy constantly arise and vanish. Some theories suggest that the entire universe may have sprung from one such fluctuation, a quantum tremor magnified by inflation into a cosmos. If so, our universe is not an exception, but a natural outcome of physics itself, a possibility realized among infinite quantum rolls of the dice. The idea that everything we see, galaxies, stars, and life, grew from a microscopic flicker of energy is both humbling and awe-inspiring. It means the grandest scales of existence may be rooted in the smallest whispers of quantum chance. Vacuum energy could drive inflation and dark energy alike. Vacuum energy is the background energy of empty space. Though invisible, it may be one of the most important forces in the cosmos. In the earliest fraction of a second, vacuum energy could have driven inflation, stretching the universe unimaginably fast. Today, it may appear again in another guise, as dark energy, the mysterious pressure accelerating cosmic expansion. If these two are truly connected, then the same energy that sparked the birth of the universe still drives its future, linking the dawn of time to the deep tomorrow. What we call nothing may be the most powerful something of all. Black holes may encode information on their surfaces. A paradox arises with black holes. When matter falls in, does its information vanish? Physics insists that information can never be lost, but black holes seem to swallow it beyond recall. One possible resolution is that black holes store information not inside, but on their event horizons, encoded in subtle patterns of quantum states. This idea reframes black holes not as bottomless voids, but as cosmic hard drives, their surfaces shimmering with hidden codes. If true, black holes preserve the record of everything they consume, woven into their horizons like runes on the fabric of spacetime. The holographic principle suggests reality is two-dimensional at heart. Building on the idea of black hole information, some physicists propose the holographic principle that the three-dimensional universe we experience may be a projection of data encoded on a two-dimensional surface. Just as a hologram carries 3D depth in a flat image, the cosmos itself could emerge from information written on its boundaries. If true, everything we see, stars, galaxies, even ourselves, might be a kind of holographic unfolding. This radical idea ties together gravity, quantum mechanics, and information theory, hinting that the deepest layer of reality may be less like substance and more like code. The cosmic web keeps growing as galaxies drift apart. The universe's large-scale structure resembles a web, strands of galaxies linked by filaments of dark matter, with vast voids between them. Over billions of years, this web has stretched and expanded, but it continues to evolve. Gravity draws galaxies along the filaments, while dark energy pushes the web outward, thinning it. As time goes on, clusters grow denser, voids grow emptier, and the contrast sharpens. The cosmic web is not fixed, but alive, slowly sculpting the fate of galaxies within it. Even now, our own Milky Way drifts along its strand, part of a larger, growing pattern. Galaxy filaments can stretch for 500 million light-years. Among the most breathtaking structures in the universe are galaxy filaments, rivers of galaxies flowing together across unimaginable distances. Some of these filaments extend for 500 million light-years, binding thousands of galaxies in a single chain. Within them, galaxies cluster like pearls on a string, their motions guided by the invisible scaffolding of dark matter. To see them mapped is to glimpse the universe's skeleton, the architecture on which all else is built. These filaments reveal that galaxies are not scattered randomly, but woven into vast structures that span the cosmos like threads of an infinite tapestry. Some of the most distant quasars are powered by billion solar-mass black holes. Quasars are among the brightest objects in the universe, outshining entire galaxies. They are powered by black holes feeding voraciously at their centers, converting matter into light with extraordinary efficiency. What amazes astronomers is that we see quasars from the universe's earliest billion years already powered by black holes with masses of 1 billion suns. How such giants formed so quickly remains one of cosmology's greatest puzzles. Did they grow from smaller seeds far faster than expected? Or were they born massive, collapsing directly from primordial gas? Each distant quasar is a beacon from the dawn of time, its brilliance powered by a monster that defies our understanding. The universe once glowed with plasma hotter than stars. In its earliest era, the universe was not cold and dark, but dazzling. It burned with plasma, a roiling soup of charged particles far hotter than the core of any star. Atoms could not exist, yet protons and electrons flew free, colliding in a constant storm. Light itself was trapped, scattering endlessly, unable to travel in straight lines. Imagine space filled with brilliance, but no clear view, just a glowing fog that stretched in every direction. This state lasted for hundreds of thousands of years, defining the young cosmos. It was a time of blinding heat and pressure, before structure, before galaxies, before even atoms could take shape. Only when expansion cooled this plasma did the universe settle into a gentler form, letting light finally roam free. Every star we see today is just a faint echo of that first all-encompassing brilliance. Recombination ended that plasma age, making space transparent. Around 380,000 years after the Big Bang, the temperature of the cosmos had dropped enough for a profound change. Electrons and protons could finally come together, forming neutral hydrogen atoms. This transition, called recombination, was like a clearing of fog. With no free electrons left to scatter photons, light suddenly had a clear path. For the first time in cosmic history, space became transparent. Photons that had been endlessly bouncing could stream outward, beginning their long journey across the cosmos. That ancient radiation is what we detect today as the cosmic microwave background, the oldest light in the universe. It is as though the cosmos took its first deep breath, opening a window to the future. To look at the microwave background is to see the moment when the universe's blazing fog parted and the first beams of light were finally free to travel forever. The cosmic microwave background is nearly uniform to 1 part in 100,000. When scientists map the microwave background, they see a glow so astonishingly smooth it almost defies belief. Its temperature varies by only 1 part in 100,000, a level of uniformity unmatched anywhere else in nature. This nearly perfect evenness tells us that the young universe was mixed and blended to an extraordinary degree, as if every corner had been stirred together in harmony. And yet, hidden in that perfection are the tiniest ripples, faint differences of density and heat. Those almost invisible variations would one day grow into galaxies, clusters, and the great cosmic web. The microwave background shows us 2 truths at once: a universe astonishingly balanced, and a universe seeded with just enough difference to allow creation. Without that delicate balance between sameness and variation, the cosmos might have remained forever featureless. Those tiny differences seeded galaxies. The early universe was nearly uniform, but not perfectly so. In some places, the density was ever so slightly higher. Gravity amplified those tiny differences, pulling matter inward, allowing clumps to form. Over millions of years, those clumps grew into clouds, then stars, then entire galaxies. It is extraordinary to think that the vast spiral arms of the Milky Way and the clusters of galaxies we see in the night sky began as faint ripples in the fabric of the young cosmos. Without them, there would have been no structure at all, no stars to shine, no planets to orbit them, no life to wonder about it all. The richness of the universe, its galaxies, nebulae, and everything we see, was written in the faintest whisper of unevenness at the dawn of time. Creation itself began with imperfection. Inflation could explain why distant parts of the universe look alike. One of the strangest mysteries in cosmology is why the universe looks so uniform across regions that are impossibly far apart. Opposite ends of the sky are billions of light years away, yet their conditions match almost exactly. How could they have ever communicated to become so similar? Inflation offers an answer. In the first fraction of a second after the Big Bang, space itself expanded faster than the speed of light, stretching tiny connected regions into the vast universe we see today. Those regions once shared heat and information, and inflation carried that sameness across unimaginable distances. In a blink, the cosmos grew from smaller than an atom to larger than a galaxy. The fingerprints of that incredible expansion remain imprinted in the microwave background, a silent memory of the universe's wildest instant. The cosmic horizon keeps expanding, but light speed keeps us bounded. Every day, light from galaxies that were once hidden finally reaches us, slowly extending the boundaries of the observable universe. The cosmic horizon grows, revealing more of the story. And yet, there is a limit written into the laws of physics. Light has a finite speed, and space itself is expanding ever faster. Galaxies beyond a certain distance recede from us more quickly than their light can travel, slipping forever out of reach. That boundary, the cosmic horizon, is not made of walls or edges. It is simply the limit of what light has had time to show us. The universe beyond may be infinite, but we will never see it. The horizon keeps expanding, but so too does what lies beyond it. We are forever inside a bubble of knowledge, peering outward, while the vast majority of the cosmos lies beyond our sight. Entanglement may link particles across cosmic distances. Quantum entanglement defies ordinary intuition. When two particles are entangled, their states remain connected, no matter how far apart they drift. A change in one is reflected instantly in the other, as though they share a hidden bond beyond space and time. Some scientists suggest this phenomenon may not be confined to small scales. It could be woven into the very structure of the universe, connecting regions of space across unimaginable distances. Entanglement may even provide a bridge between quantum mechanics and gravity, helping to explain how space-time itself emerges. If this is true, then the cosmos is threaded with invisible links, binding stars, particles, and perhaps even galaxies in a subtle quantum fabric. To live in such a universe is to exist in a web of connections deeper than distance, a cosmos where separation may only be an illusion. Space-time itself may be emergent from quantum information. We tend to think of space and time as the foundation of reality, the backdrop against which everything unfolds. But some physicists suggest they may not be fundamental at all. Instead, space-time might emerge from patterns of quantum entanglement and information, as though the universe were woven from invisible threads of data. In this view, geometry, distance, and even gravity are large-scale effects born from countless microscopic exchanges of information. The cosmos would not be a stage, but a story written in code, with space-time as its unfolding plot. If true, then our universe is more like a hologram than a solid object, a grand projection of hidden relationships. The deepest layer of reality might not be matter or energy, but information itself, endlessly recombining to give rise to the world we know. The universe is still ringing faintly with primordial vibrations. Long ago, the young universe was filled with sound, pressure waves moving through the hot plasma like ripples in a vast ocean. Those waves left their imprint, freezing into the structure of matter as the cosmos cooled. Today, we still see their faint signature in what are called baryon acoustic oscillations, enormous ripples in the clustering of galaxies. They stretch across hundreds of millions of light years, like the frozen echoes of creation. To measure them is to hear the aftersound of the universe's first moments, a cosmic hum that continues to shape structure even now. Though no ear can hear it, the cosmos is still ringing with vibrations from its birth, faint yet enduring, carrying across billions of years. We may never know whether our cosmos is the only one. The multiverse is one of the most tantalizing ideas in science. Inflation may have created not just one universe, but countless bubbles, each with its own laws of physics. Quantum theory hints at branching realities, while black hole models suggest new universes might bloom on the far side of collapse. Yet, by definition, these other universes may lie forever beyond our reach, cut off by horizons we cannot cross. Perhaps our cosmos is one of many, or perhaps it is truly unique. We may never know, and that uncertainty is part of its beauty. The fact that the universe inspires such questions, that it invites us to wonder about realities beyond our own, is itself a profound gift. To live in a cosmos that holds mystery is to live in a place where imagination and science meet, stretching toward infinity together. And so, our long journey through the universe draws to a quiet close. We've drifted across billions of years, from the first hot glow of plasma to the faint whispers of primordial vibrations that still echo through space. We've wondered at horizons we cannot cross, at galaxies born from ripples smaller than a whisper, and at the possibility that our cosmos is only one among many. Cosmology reminds us that we are woven into something vast, something that began long before us and will continue long after. Yet here you are, breathing softly in the present moment, carried by the same laws that guide galaxies and stars. Every heartbeat, every breath is part of that story. So now, let the questions drift like leaves on a gentle stream. There is no need to hold them. The universe will go on turning, stretching, and singing its quiet song, whether you think of it or not. You can simply rest, knowing you have touched its mystery tonight. Thank you for sharing this journey with me. If you've enjoyed it, you can gently like, subscribe, or leave a thought in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing more to do. Just allow your body to sink deeper into rest. Let the day fall away behind you, and let the calm widen within you like the open night sky. The universe is vast, and so are you. Sleep well, and I'll see you in the next video.